Hey everyone, James McBride here. Let's take a look at a little more wireless information. There's a lot of wireless information, and that's for a couple of reasons. When you think about what you're doing with wireless, it's really like this bus network. You can't have everybody broadcasting at the same time. Otherwise, the signal just jams up. So you have to have all these control mechanisms to make that happen. And then you have to try to figure out how can we get more throughput? How can we get more bandwidth so that our ever increasing demand on the internet, we're able to do what we want to on that it doesn't stay slow. How do you make that happen? Well, we're going to take a look today at what's the difference between a small network and a larger network. So the small networks we call SOHO, which is a small office home office. In other words, it's just a building. It's just one building, and you've got maybe maximum 40 different nodes or hosts on that network, and that's about it. So SOHO wireless, let's take a look at the two ways that this is implemented. You have a wireless router, that's what we call them. However, this is really, right, a wireless access point, router, switch, firewall, right? That's a lot of things in one. And I love the fact that this is showing the back of it. So we can see the access point, the antennas here. We can see the switch portion, and we can see the router portion over here. And these, of course, are USB, so you could share out some hard drives or something. This would be placed in the house. Here we're seeing it right here in this one location. And this is a fairly good-sized home. So that would mean anything that's near it is going to have no problem getting to that access point. Anything much further away is going to have some difficulty getting there, depending on the materials that this is made up of. But this is the standard setup with a central access point, normally called a wireless router. And of course, that's going to be placed where this goes out to the internet, wherever you can physically plug in that cable and have it go out. Now, the other setup that's becoming popular but is really expensive is mesh networking or a mesh setup. And the mesh setup basically has one of these. One of those is the actual router that's plugged into the wired connection that sends the data out. And then the other two, you actually just place around the house or office so that you have a much better coverage of an area. This is really going to cover well. But these are talking back and forth to each other and transmitting the data basically back to this main hub. Again, that's more expensive. The other option within a standard setup, which is very common, is let's say that we are getting a great connection through here. So we're really connecting everything but this computer down here, which is heavily used, we'll say, and it's really not connecting well. It's just not connecting well. Then they would normally put some kind of little repeater in here. And a repeater is a little wireless thing that you plug into some power source. And then you tell it the actual router is over here. It's on this channel. Go ahead and connect to it. You give it all the passwords that it needs. And then it actually takes this wireless network name and promotes it on a different channel. So it's not interfering with this one. So that's common. You can have a router and then you get a little repeater and it repeats out. Where this does not need any repeater because they're doing the repeating and they're all connected talking to each other. So you got those two setups for SOHO. But what about businesses that cover a much greater area and often cover a lot more nodes or hosts? Like EAC, we've got thousands of hosts that are going to talk on that wireless network. How do we make that happen? Well, first off, the equipment on the back end is going to be different, but we're going to need different naming conventions in order to have this all be one network. SSIDs are a service set identifier, and guess what? This has an SSID, and so does this. I was using the term wireless network name or network name. That's very common for us because most people are like, SSID, what's that? But that's what it is. It's an SSID. It is a human readable, up to 32 characters, letters and numbers, no problem. And it's part of the frame header. That has to be. It doesn't matter what network, you got to have this SSID. It associates you with an access point, with a network. So at home, if I call it McHome, If that's one of my Wi-Fi's, and I said it's MIC home, then that's the SSID. And on the computer, it's going to see it. It's going to say MIC home. I'm going to click on it, and then it's going to say, what's the passphrase? Once I put in that passphrase, then my frames are going to be sent out with this header saying, I go to this network. I go to this SSID. Works great. Works great for a small situation. But in a large situation, we need more. So the SSID, that's the name of a network that you're seeing. And then we have a basic service set identifier. And that basically is the MAC address. Not basically, it is the MAC address. So what's happening is you have these in a situation like EAC or any school or any big place, they're going to have these different access points that go back into a control box someplace. And so these access points can actually, on the back end of this, see each other. They can see each other through that cable. And you'll have a bunch of these all over the place. Well, how can I communicate with this computer? See, the problem is that this computer way over on the end is still going to see the signal from here. It's not going to be great. It's going to be low. And this computer needs to be smarter and connect to the one that's nearer to it. So how does this get the appropriate information to this AP instead of this one? How does it happen? Well, during this negotiation process, it's going to say, oh yeah, I'm part of EAC StudentNet, whatever, whatever. And it's going to see the signal and it's going to say, oh, this is a stronger signal. So I need to connect to this one. If it has an error with it, I'm not joking, on the backside, these can talk. And this one can say, I'm really getting a weak signal from this. I'm going to hand it off to you. So you talk to this computer. What is it using? MAC addresses to do that. So then it's saying, hey, you need to talk to me. And my basic service set identifier is my MAC address. So talk to me. Then, in order to group the whole thing together, you have this extended service set identifier. And that's what they're showing here, is that you really are putting this all together in this extended service set that's really going to tell it, I'm part of this bigger institution. And that's how it works in a large environment and what we would call an enterprise, because you want your customers, your employees, to be able to roam through wherever they're going and not have to retype in passwords, passphrases, connect to a different box, how they used to have to do it. And I don't know, because I wasn't around back then, but what they would have had to do at EAC back before this stuff was really put into play is they'd have access points. And if you were over in the dorms, then that would be a different Wi-Fi. You'd have dorm Wi-Fi, dorm EAC Wi-Fi, and you'd connect to that. And then you would go over to someplace else, and that would be part of EAC StudentNet, and you connect to that. And yeah, once you get all those connected, it's not bad for the user. However, yeah, it's hard to manage on the other side of that, having to deal with all these different boxes, all these different passwords, all these different setups. This really provides any institution, even a smaller place that may be spread out. So even if you went to an organization that only had 40 people in it, but they have a larger campus, they have a much more spread out area that they're covering, then they would use some heftier stuff that would allow these boxes, these access points, to talk back and forth and have this set up so you can roam around in this environment without a problem. So they want you to understand that. They want you to understand, hey, there's an SSID, that's the name of the network. There's also one that covers the entire network in total. And then there's an SSID that is just to talk to that particular AP. And that's important because the computers will need to say, I'm part of this ESS or this ESSID. So this isn't going to change for me, but this basic service set identifier is going to change for me. And that's okay, right? It can do it. You've already continuing our quest for understanding of Wi-Fi. Let's take a look at some standards. Down here, you'll note 802.11n, 802.11ac, 802.11ac, 802.11ax, and so on, right, as we come down. Basically, this 802 thing is an IEEE designation. They all got together, basically smart people that were dealing with networking. They got together in 1980 in February, that's the 802, and they discussed networking and the different ways it could be done. because there was a lot going on. Different companies had already started doing this, were already selling equipment. And then there was the idea of, we really could get further if these companies were following set standards that we can all agree on. That way, these networks can be more compatible. So 802.11 deals with wireless. That's what it deals with. And it was not added in the 80s, it was added later. That's why you see this designation, because 802.11 is the wireless standards, and then they add a letter on the end of it. Nowadays, we're starting to get more into these marketing terms of Wi-Fi 4, 5, 6, 6E, 7. I don't much like that, but it is what it is. Basically, in the past, you would look and say, well, I'm using 802.11 AC, and AC would then use 2.4 and 5 gigahertz. That's why you see it listed here. In any case, it involved a lot more than just what frequency you were using for the wireless. It also involved how and what way you were communicating. So as time went along, we were able to get more and more bandwidth or more and more throughput for this Wi-Fi. And Wi-Fi really has a restriction. You have a wave that you're using, and you can only encode so much on that wave that you're using. So how do we get more out of it? Well, one way is to decrease the amount of checking we have to do, because there is a lot of checking that has to happen in Wi-Fi because it's on a bus style network. So better controlling mechanisms from the APs themselves, we can do that. We can also change how we're encoding on that wireless, but only to a point. That's only going to help to a point. And the other thing we can do is band these together or combine these frequencies together and use one solid network with multiple frequencies, which is what they're doing with your cell networks. So when you go from 3G, 4G, 5G, and all this stuff, they're doing a lot of stuff. I don't want to make it sound like this is all they're doing. But the biggest thing they're doing is strapping in other radio frequencies so they can push more through there. So to break this down, I have a wireless router that is compatible with 6. When you start talking about using these standards, you have to realize that both sides have to comply with the standard. So if I'm really, really going to use this technology, which gives me up to 9 gigabits per second, right? That's a lot. So if I'm really going to be able to use this, the device that I'm using, like a phone or a computer, has to be 6 compatible, and the router has to be, or access point, has to be 6 compatible. Now, I have a bunch of devices that are not 6 compatible. The 6 came out several years ago, but it takes people a while, especially when, if you're using 5 and you're getting 1.3 gigabits, then, you don't care too much. So basically what's happened is there is a bunch of technology that's sold, that's smart technology, a little turn this on, turn this off, and they're not AC compatible, they're not AX compatible. In other words, Wi-Fi 5 or 6 compatible. They're not at all. They're only this N compatible, which is 600 megabits. So because you're dealing with a bus network, because everything is on this network as a bus, it's really, really hard to say, okay, we'll use this old technology for this little switch out here that turns the lights on and off, and then we'll use this new technology for the devices that understand it. Instead, what you end up doing is none of these devices work. So you move to the 6 standard, and then the device is like, I can't connect. I don't know what to do. And that's a problem. So at my place, right, because it is 6 compatible, and I would love to move to that. But what it provides is 2 5 gig channels and 1 2.4 channel, meaning that I can set up 3 separate networks off of this, or I could combine all those into this 6 standard. But again, the devices have got to be compatible with that. So I don't do that. I have a 2.4 network that most of those are connected to, and then I connect phones and TVs and game systems all into one of the two 5 gigahertz because you can do two that are non-overlapping. We'll look at that in just a second. So when you take a look at the standards that are out there, note that they're moving to these numbers, Wi-Fi 4 and so on, but the text should be talking to you about whether or not this is 802.11ac, what speed it is, and what frequencies it's supporting, right? And AX and what it's supporting. Now, there's a ton of detail that I'm not going to get into in this video that talks about how it's communicating or being able to communicate with two different devices on different channels. And there's some really fancy stuff going on that's going to push us into the future. The main thing that you need to really understand about this, a very practical, that if you go out and say, yeah, I got this new AX router and my phone's AX compatible, I'm going to set it up. Your phone will work great with that and nothing else will. It will come up with errors saying that it can't connect. Eventually, hopefully, I think we'll get around that. One way to get around it is to buy a really cheap router, which I haven't done, but buy a really cheap router for all those things that have to connect, and you put it on some network that's, they can all connect in through there, and then you plug in the switch ports on the back of your two Wi-Fi access points, and you set the other one to just do the max that it can do if you've got compatible devices. So here you go. Down here in gray, we've got Bluetooth because it's important to note the Bluetooth is running on a 2.4 gigahertz frequency, but its design is different. It's not really meant to push traffic through other than some sound to speakers or to headphones or to a printer or something like that. All right, let's talk about channel overlap. Channel overlap is this process of what I was talking before. I can have two 5 gigahertz non-overlapping. This is what happens. So when you're using 2.4 gigahertz frequency, then you're using actual channels within that. Yeah, just like FM, AM channels. And you can see this one is 2.412, 2.417, 2.422. The channels are lined up next to each other, going all the way up to this 14 in some situations where it's 2484. Now, what that means is that basically your channel overlaps into others. There's just no other way to say it. These broadcasting ranges bleed into the ranges next to them. If you were to go into a location and say, I'm going to put mine on channel 2 and somebody's on 4, you're hitting them. You're going to barely hit them, right? 2 comes over like this right here. So you're barely interfering with 4. You can probably see it better in the orange. In other words, in a very congested location, there'll be tons of people all over these channels. Now, the way it works now is most stuff auto. So your little access point router will just try to figure it out. It'll just look for, oh, where can I fit in here? And it'll dump itself in there. And that makes it easy for people to use. But you are trying to learn beyond that, right? You're trying to learn how this stuff works to secure it. You're also trying to learn how it works so you can troubleshoot it. So if you are somebody setting this up at your house, you would want to run basically a wireless survey and find out who's using what and where and what the strongest signals are on, because a lot of times your little access point is not picking the right ones. It's doing the best it can, but it's not picking the right ones. A very, very good example would be if you have some big windows in your kitchen and you sit at your kitchen table all the time and you use Wi-Fi all the time, and that's where you're doing your work all the time, and you notice, man, why is my connection slow? But then when you're in the living room, it's never a problem. Well, if you did an actual survey and looked at what was happening, see, because your router is not sitting next to you in this scenario, where it's at, it thinks, say, for instance, channel 6 is the best to use. But you're sitting next to the window and your neighbor across the street is blowing his channel 6 into you, and it's really messing with your signal where you're at. See, that's one of the problems of wireless, is the fact that you could have somebody disrupting your signal, because it's not just a matter of where the signal is coming from. It's also a matter of where you are, because you have to talk to that router. So what this is trying to show you is, hey, look, you can set up, for instance, something out here on channel 2, and it's going to come over here. And then it would be great to set up something on channel 8, and then that wouldn't conflict, and then something way over here. That way you're not conflicting with the other channels. Once you start to conflict, then you start to compete in the airwaves, because again, it is a bus network. It's not a switched network. And then it's whoever has the biggest signal, right? Whoever is amplifying that the most. Probably the best example I can give of this is I had a friend who lived in an apartment complex, and she was like, "Man, can you help me out? I'm in like in the next room, and I cannot pick up my wireless signal." That's pretty bad. It's an apartment. It's not that big. It was a one-bedroom apartment. It was pretty small. And everybody had their own wireless access point. So when she's in the bedroom, she's getting blown out through the wall by her neighbor's router that's sitting right next to that wall on the other side of that wall. And of course, that's going through that wall and then being downgraded as it tries to get through the next one where her router is sitting. And it thinks, oh no, we're good. We're good on that channel. So I had to do this wireless survey, and the thing was just packed loaded, and then find one that was weaker. And so I did. I found out that on channel 3, that's where the weakest signals were, that they were out there someplace in the apartment complex, but they weren't directly interfering. And that improved her throughput, because if she wasn't getting bombarded with the same exact channel. So you got to realize that this is 2.4 and how that looks. And they want you to know that, how many non-overlapping channels can you have? So always use 1, 6, or 11 only in 2.4 gigahertz band. Well, that's not really true. You're assuming, right? I want these, they're far enough separated and they won't hurt, but your next door neighbor may be using 1. And so you don't want to use 1, right? You want to move over. Let's move on to our 5 gigahertz. Now, 5 gigahertz the frequency is smaller in a 5 gigahertz frequency. That means that you can have more non-overlapping. So there's 21 non-overlapping 20 megahertz channels. Now, when they're talking about this 20 megahertz, they're talking about the width. And that gets confusing to people. It's like, wait, you're using 5.35 gigahertz for this. What do you mean 20 megahertz? Where the crap is that coming from? That's the width. So you can actually say, okay, if I'm only using a 20 megahertz channel, that's the width of that channel, then I've got 21 of those that I can fit within the spectrum and not overlap. Now, that adding this width to it is really what gets you to the throughput that they're talking about here, these maximum speeds. If you're really saying, I'm going to get 9.6 out of this, then you're using all the standards capable in this 6E to get you to that point, which means you're going to be running up here at 40 megahertz and 40 megahertz, right? Creates a channel planning problem similar to 2.4. When you get to basically throwing in this 40 megahertz, you've got 149 you can pick from, or 153. And then you've got 157 and 161. So at my house, right, 5 gigahertz doesn't go that far. So my neighbors aren't really going to conflict with me on this. So I've got 1 5 gig doing this, 1 5 gig doing this, and I'm good to go. But you only get 9 of those 40 megahertz that are not overlapping. So I've got 2 that they're not overlapping. They're great. They're these channels that are doing their thing. Am I getting the max out of that? No. I would have to combine those 2 channels under one network name with the 2.4, and then I would get all that throughput. So overlapping on this stuff is important to understand. And it's not hard to deal with. Like I said, you can deal with it in a situation that's really got a ton of wireless networks out there. So you can deal with it in just about everything. But what you're doing is a network survey that will show you this is strong, this is weak, and I'll put my channel that's strong over the weakest one. That way I don't have a conflict there. So that's Wi-Fi channel overlap. And then propagation that we talked about before. I figured what I'd do is that now that we've gone through overlapping channels and trying to understand that when you're using these technologies, it's binding together multiple channels and different frequencies into this massive one data channel path. then okay, the heat map, let's go back to that. This heat map is going to show where is this radio signal blowing out. This is an actual advertisement for some heat map. And heat maps are weird in a way because I would expect a heat map to show the strongest. And that's what this is. It's showing where the signal is the strongest. It's hotter there, right? But some of them are actually just the opposite. And so the red will be out here and so there's not really a huge standard on that, but I did try to find one that was like, hey, this is a heat map. This is where your biggest coverage is. You can see it blowing through here. This is going to go downstairs, it looks like. So it's hitting here. Then it's getting pretty weak as it gets lower. This area in green means, wow, it's not good. It's actually getting pretty bad, but you're probably still got a okay connection here. And then you've got this, right? You're getting this in through the door. So you're getting the signal in through this door, and it's yellow right there, and it's bouncing around and becoming green. Same here, getting in through this door, yellow, bouncing around, green. Same here, getting in through this door, bouncing around, green. But you have to go through so many walls that if you're sitting in the bathroom, that's your water closet right there. But you're sitting in here, that signal is really, really, really weak because it's going to have to come in and bounce around, go through here, bounce, 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 come to wherever you're at, and then bounce back out to here. So it's good to see a heat map or how that wireless signal actually propagates through a building. And when you start using these different technologies, then if this was a 5 and 2.4 combined, this is about where the 5 is going, and that's all the 5's hitting. So it's not going to be great if you're saying, I'm on a 5 network, but I'm out here in the yard. That's not going to work for you. As a matter of fact, in my house, it doesn't work, right? I usually tie my phone to 5, and it can kind of pick it up outside, and I have to switch to the 2.4 because that's got a better signal strength because of the width of that radio wave. Of course, if I was using the brand new technology, all the AX stuff, what it would do is auto figure that out. And so I'd just be on the network and it would just start using just 2.4 because that's what it can get. That's the nice thing about using these newer technologies. Again, the drawback, well, if you've got stuff that can't function at AX, then you can't use it. You got to use something else. All right, so that's propagation, heat map. There's a lot of those out there that you can take a look at. And there's software. There's a lot of software that provides that. There's some that'll let you do that for free. This kind of software is heavily used within commercial environments because they're going to place those antennas all over the place. And so they'll run this software, put the antennas up and run it and see what it's looking like. And then let's talk about the last thing here, shaping the signal. This is an omni. An omnidirectional antenna sends the signal out all sides in a circle. This is what an omni signal looks like three-dimensionally. So if we could view the actual Wi-Fi being sent out, it would look like a donut that's being blown out that way. This is a top-down view. So you would have the antenna here and it's blowing out. It's blowing out like that. This is a directional. So what you're trying to do with a directional or a Yagi is a super directional, it's like really small, is take the energy that's being blown out in an omni. And why we talk about the omni is because, let's go back to here. These are all omnis, right? Those are omnis. So that's how most routers are working. They're doing this. Let's say we want to focus or concentrate that energy. If we do that, we could get it to go further. So instead of all in a big circle, we can take it and push it a certain direction. And that's what this directional is doing. And you see these directionals and these omnis used in any kind of radio wave communication. Old school CBs, right? It's just this big tower, and that CB radio is running off this huge omni, goes everywhere, just covers the whole county, basically. And then you'll also see these where, oh, I'm trying to hit that tower way over there, so I've got to push that signal as far as I can. So this is the three-dimensional view of what it would look like coming off of a directional like that. And then, of course, the top-down view. Notice you do get some bleed out that happens along those lines. But really, that's the last thing I wanted to show you within this material. just so that you can understand that you can shape the signal to tell it where you want it to go. And that's important when you're dealing with security. The placement of these antennas for security purposes is important. If this was a business, you would understand that anybody right over here is getting a great connection. That means if this is sitting in the parking lot, that might be a security issue. That might be a security issue. Maybe you should move this more towards the center here, see what that looks like. Maybe over here, because you don't want it in the parking lot so much as the back, which has nothing. That's the kind of thing you have to think about when you're talking about propagation and shaping the signal. A lot of places do that. They shape the signal. In EAC, you don't have omnis. So if you're here at EAC and you look up on the ceilings, I'm always pointing to those things. It's a panel. It's basically a directional, is basically what it is. And it's pushing this out downward. So it's coming out like this. And it gives great coverage. And then there's another one in the hall and so on and so on. But you would still want to look, say if you had a very, very long building, we'll give you an example here. Say if you're over in the AP building and you want that signal going all the way down the hallway, but you want to decrease the signal going out to the public, then you would put a flat panel on the wall and push the signal down that hallway so it would not go out as much into the open. Now, EAC is obviously not worried about that because it's a network for the entire campus. They would be more concerned if for some reason you stuck a directional right up here on my wall behind me and it's pushing straight out the windows that are right over there. That would not be good. You'd be hitting like 3 or 4 houses way over there. But in businesses that do not have this open network that basically all these students are on, they have a closed network and it's only really for their employees. You will walk into their facilities and see very directed Wi-Fi so that they can reduce the probability of somebody hacking on the outside, not just providing the best coverage of the building that they need, but trying to make sure it stays in that building. All right, questions, let me know, and thanks for watching.